Mathematical numbers are the least abstract things there are. I mean, think about this. Bottles are a pretty abstract concept. I mean, this bottle has nothing to do with this bottle. I mean, think about it. They have different shapes, they are made from different substances, and their purpose is to contain two different things. This bottle has more to do with a balloon than this. Yet, we call both of them a bottle. On the other hand, numbers are just numbers. 3 is always equal to 3 and nothing else. That's why mathematics is the least abstract thing out there. But if we want to use mathematics in the real world, then we have some real problems, because then abstraction really kicks in. When we are talking about real world things, then it's abstract. For example, 3 knives, or 3 batteries, or 3 murderous robots. That's pretty abstract. And so that's why we usually try to fix this abstraction. And the best thing we came up with to fix this abstraction is units. And so here we should discuss custom units. Why are they useful and why they are worse? So, let's imagine you are stranded on some sort of island and there is no civilization next to you. No rulers, nothing of some sorts. Now, you want to build a boat. And because of that, you probably need some measurement system. But you don't have a ruler, you don't know how long a meter is, so what you can do is you can take just a beer bottle and set it as your custom measurement system. Now your units will be beer bottles. And because beer bottles are generally really similar, adding them two together gives you a unit of 2 beer bottles. And this works. I mean, it does. It is actually a decent unit system. But it has some problems. So let's go back to the first example. Let's imagine they crashed on some sort of island. And on this island you only have beer bottles and a book on how to build a ship. Now, using those beer bottles as measurement system, you can build a ship. It would probably take a bit of work, but in the end you would end up with a ship. Now let's imagine that you take this ship, go sail home, and during your travels the ship would crash and you once again end up on some sort of island. Now on this island you do not have a book on how to build a ship, but you still have some bottles. From them, from memory, you can create the exact same ship. And you start building the thing, but you are unaware of a problem. You see, these beer bottles are a tiny little bit bigger. And whilst 2 beer bottles might seem the same, the small differences add up and in the end you get huge differences in distance. That is the problem with custom measurement units. They are usually poorly defined and because of that, they are very not precise. Now there are 2 ways to combat this problem, the simple way and the correct way. Let's start the simple way. We can create some sort of object made to represent the unit in question. For example, an object which weighs exactly 1 kilogram. Now this is relatively easy to do, but it has 2 problems. The first problem is the issue of using a material object for it. If you'd like to order something from Japan, for example, and you'd like it to be exactly 1 meter long, then in order to make sure that this thing is exactly 1 meter long, you should send your 1 meter long object to Japan, which is a rather suboptimal approach for obvious reason. Now obviously you could just create multiple meter long objects and send them around the world, but then we can see the other issue of a problem, which is deterioration. The more you use these objects to measure a perfect meter or a perfect kilogram, the more wear they sustain, resulting in less precise measurements. That's why this method is simpler, but worse. On the other hand, the more complex but correct way looks like this. You take the unit you'd like to have in your system and you define it in relation to some physical constant, preferably something that is always equal to the same thing and can be measured independently anywhere in the world. Now that's how the base 7 units in the SI system are defined. Starting with time. Time is defined in relation to the cesium frequency, the natural resonance frequency of the cesium atom. Which means that if you measure that frequency 9,192,631,770 times, then you know that exactly 1 second has passed.
For meters, we use speed of light, the most constant of the constants. The process here is rather simple. With seconds already defined, we just take the distance the light has traveled in 1 second and divide it by 299,792,458, and that fraction would be equal to exactly 1 meter. Mass is defined in relation to Planck's constant, the amount of energy a photon or a particle is able to carry. It is defined in joules, and in order to get the mass from it, we just have to transform it. A lot. But with the length and time defined, it is not only doable, but also rather simple. Ampere is the cleanest of them all, defined as 1 coulomb per second, coulomb being 6.241509 times 10 to the 18th atomic units. Per second, that's an ampere. Rather simple in comparison to the others. And here we start getting into the muddy territory with Boltzmann constant and a Kelvin. Now, explaining this at this point would be rather pointless because I just simply do not have the time to get into what the Boltzmann constant is and how to define Kelvin based on it, so I'll just show you the equation. We went through 5, 2 more to go, and listen. Luminous intensity and amount of a substance are different. First of all, because luminous intensity is rare and very complex, the most complex of them all, and mole, the amount of the substance, is pointless. 1 mole represents 6.02214076 times 10 to the 23rd power elementary entities. What does it mean? Well, it means that if you have 1 mole of something, you just have this number of entities. There's no constant required, it's just a number.
Having a mole in your system is kind of like having a unit which would be called pointon. And this pointon would represent 5 things. So for example, a pointon of apples would be 5 apples. A pointon of cubes would be 5 cubes, and a pointon of cylinders would be 5 cylinders. It's really more of a constant than a unit. It's not really a physical constant even. For now, that'll be it. Thank you so much for watching, and have a great day. Bye!